Hi, I'm Josh Allman, and today I'm going to tell you about the paper Kronecker Products, Low Depth Circuits, and Matrix Rigidity that's in STOC 2021. So this paper contains a lot of results that relate these three notions together, but at a high level, the main idea of the paper is to take this notion called matrix rigidity, which was originally introduced as a lower bounding tool, and instead use it to design upper bounds. So we, in the paper, we prove matrix rigidity upper bounds and use them to prove upper bounds in other models of computation, like faster algorithms and smaller circuits. So in this talk, I'm going to focus on one result in particular, which uses matrix rigidity upper bounds to design smaller low-depth circuits for the Walsh-Hadamard transform. Uh, but at the end of the talk, I'll mention one other result in the paper, and there are even more results that I won't have time to talk about here. Okay, so I'm going to start by defining the circuit model we'll be talking about, the low-depth circuits, and then I'll tell you about Kronecker products, which describe the matrices we'll be dealing with today. And then after I tell you about the result, I'll talk about matrix rigidity and how to use it to design smaller low-depth circuits for the Walsh-Hadamard transform. Okay, so the circuit model we're dealing with is called linear circuits. So these circuits are over a field F, and you can, for this talk, think of the field as the complex numbers. Though the results I'll talk about today work over any field. These circuits have n inputs that I'll call x1 through xn, and n outputs that I'll call y1 through yn. So they take in n field elements, n complex numbers, and they output n field elements or complex numbers. Each gate in one of these circuits computes a linear combination of its inputs. So one way you can think about it is that along each wire in the circuit, there's a field element like a complex number written. And then what the gate does is that it takes in the complex numbers described by the inputs and computes their linear combination weighted by the numbers fixed along the wires. So each gate computes a linear combination of its inputs. And so in particular, because of that, all the outputs are also going to be linear combinations of the inputs. So every linear circuit computes a linear transformation. So you can think there's a matrix M that's an n by n matrix, and such that the outputs y are going to be m applied to the vector of inputs x. So how do we measure like how complicated one of these circuits is? Well, there's two measures. There's the size and the depth. So the size of one of these circuits is going to be the number of wires in the circuit. So we'll allow for gates that have unbounded fan-in, but we'll count each wire in the circuit toward the size. And then the depth is the length of the longest path from an input to an output. So in this example here, there's a path of length 1, 2, 3, 4. So this is a circuit here of depth 4. And in general, the depth is the length of the longest input-output path. So what do we know about circuits like these for matrices? Well, every matrix has actually a depth 1 circuit whose size is the number of non-zero entries in the matrix M. You can just connect every input up to every output and put the weight on the edge equal to the corresponding entry of the matrix. So you have an edge whose weight is the ijth entry of the matrix, pointing to the output yi coming from input xj. And then you have one edge like this for every non-zero entry of the matrix, and you can check that this correctly computes the matrix M. But in general, the question we ask about these circuits is, when does a matrix have a smaller circuit than that? So like, for example, every matrix has an n-square size circuit. When do matrices have smaller circuits than that, and how much depth do you need to design such circuits? Okay, so the matrices we're going to focus on are defined in terms of Kronecker products. So here's the definition if you haven't seen it before. So if you have a matrix X that's an A by B matrix, and a matrix Y that's a C by D matrix, their Kronecker product, that's written like this, like with an O times symbol, is an AC by BD matrix, whose entries are given by this expression. So there's a row of the Kronecker product for each pair of a row from one from each matrix, and there's a column in the Kronecker product for each pair of a column from each of the two matrices. And then the corresponding entry in that row and column of the Kronecker product is the product of the values at those two entries of the matrices X and Y. So for example, here are two 2x2 matrices, so their Kronecker product is a 4x4 matrix, and you can see that for each pair of an entry from the first matrix and an entry from the second matrix, there's an entry in the Kronecker product whose value is the product of those entries. So this is a Kronecker product. It's a nice way to sort of recursively define matrices. And the most standard example in the matrix we'll focus on today is the Walsh-Hadamard transform. So it's a family of matrices defined like this. So the first one is a 2x2 matrix with 3 1s and a -1. And then in general, the nth Walsh-Hadamard transform is the nth Kronecker power of H1. So like the Kronecker product of n copies of H1. So it's a 2 to the n by 2 to the n matrix whose entries are all 1s and -1s. Here's a picture of the first few. You can see that each one looks like 4 copies of the previous one, except that the top right entry is negated. Okay, so if you haven't seen the Walsh-Hadamard transform before, it comes up in a lot of different contexts and algorithms and complexity. One notable example is that the Walsh-Hadamard transform is actually the Fourier transform over the Boolean hypercube. So what I mean by that is, if you have a multilinear polynomial p in n variables, and you can form the vector of its coefficients, so it might have up to 2 to the n monomials, so you make its vector of length 2 to the n of all of the coefficients of the polynomial, then multiplying the Walsh-Hadamard transform times that vector evaluates the polynomial on all points in -1, 1 to the n. So it evaluates a polynomial on all the points in the Boolean hypercube. So this is the Fourier transform for the Boolean hypercube that you might have seen before. Okay, so what do we know about circuits for this Walsh-Hadamard transform? Well, there's a nice standard kind of recursive algorithm called the fast Walsh-Hadamard transform that shows that it has a depth d linear circuit of size d times n, the side length, to the 1 plus 1 over d. So for example, plugging in depth log n, you see that it has a depth log n and size n log n circuit. If you plug in depth, say 2, it has a size n to the 1.5 circuit. So if you're familiar with like the fast Fourier transform algorithm, this is really similar to that. It's actually a simpler version of the fast Fourier transform algorithm. It sort of follows without too much work from the recursive definition of this transform. And the result I want to tell you about today is a new, smaller circuit than this for the Walsh-Hadamard transform for any small depth. Okay, so let me tell you the new result. The new theorem is that over any field, the Walsh-Hadamard transform has a depth 2 circuit of size just n to the 1.48, so improving on n to the 1.5. And more generally, has a depth d circuit of size d times n to the 1 plus 0.96 over d, instead of 1 over d in the exponent. So this is, I think, exciting in its own right to design a smaller low-depth circuit for this family of matrices, but it's also particularly interesting in light of known barriers for designing small circuits for this transform for a restricted type of circuit called bounded coefficient circuits. So a bounded coefficient circuit over the complex numbers is a circuit in which the coefficients in the linear combinations computed at each gate have at most constant magnitude. So remember, in a linear circuit, each gate is computing a linear combination of its inputs weighted by the numbers that we rate along the wires of the circuit. And if we restrict the numbers on the wires to be complex numbers of constant magnitude, then we get a bounded coefficient circuit. So for example, if you've seen the fast Fourier transform algorithm before, you know it involves like multiplying by a lot of particular roots of unity throughout. So when you convert this into a linear circuit, the numbers along the wires end up being these roots of unity which are all complex numbers of magnitude 1, and so you get a bounded coefficient circuit in that way. And more generally, the best known circuits, at least that I knew, for the Walsh-Hadamard transform and Fourier transform and so on, all were bounded coefficient circuits before this work. And there was a line of work in the 70s and 80s and 90s trying to explain why explain why we haven't been able to design smaller circuits for those matrices. And they showed barriers. For example, this result by Pudlock in 2000 showed that bounded coefficient circuits for the Walsh-Hadamard transform couldn't improve on the fast Walsh-Hadamard transform that I mentioned on the previous slide. So if you restrict yourself to bounded coefficient circuits, then in depth 2, you actually need size n to the 1.5. And more generally in depth d, you need size d to the times n to the 1 plus 1 over d. So our new result overcomes this barrier by using larger coefficients as part of the circuit. And we end up using coefficients whose magnitude is like n to the power of a small constant. Like I think something like n to the power of 0.25. So I think this is, as far as I know, the first non-trivial upper bound circumventing one of these bounded coefficient lower bounds that started from a work of Morgenstern in the 70s, who showed such a result for the discrete Fourier transform. But I think it's interesting that even though this matrix is a very natural matrix with just ones and minus ones in it, we can actually use large numbers in our circuit to design smaller circuits for it. Okay, so let me tell you a little bit about how we prove it. I won't be able to get into too many details in this talk, but the main idea is to make use of matrix rigidity upper bounds. So what is matrix rigidity? Well, we say that a matrix is rigid if it's far from any low-rank matrix in Hamming distance. So there's of course some parameters involved. So either the rank R rigidity of the matrix M, denoted like this, is the minimum number of entries of the matrix that you have to change to make its rank at most R. So let me give some examples. So if you look at the n by n identity matrix, then for any rank R, its rank R rigidity is n minus R. That's because you can change n minus R of the ones along the diagonal to zeros, and that will make its rank R. In fact, among all full rank matrices, the identity matrix is as not rigid as possible because you can keep changing one entry from a 1 to a 0 to decrease its rank by 1. By contrast, a random matrix is known to be very rigid with high probability. So for example, a random n by n matrix over F2, with high probability, you have to change a constant fraction of its entries to make its rank slightly sublinear. So to make its, for any like sublinear rank, you with high probability have to change a constant fraction of its entries. So a random matrix is very rigid with high probability. The identity matrix is not very rigid. So rigidity was introduced in the context of linear circuits by Les Valiant in the 70s. And he showed that any matrix that's computable by a linear size log depth arithmetic or linear circuit has this rigidity upper bound. So for any epsilon, you can change n to the 1 plus epsilon entries of the matrix to make its rank sublinear, like n over log n. So he showed that any matrix that has small low-depth circuits is also not too rigid. So this led to a program of trying to prove that certain matrices of interest are rigid, which would imply that they don't have small low-depth circuits. For example, I mentioned before, the Walsh-Hadamard transform has n log n size log-depth linear circuits. So if we could prove that it's more rigid than this, then that would work towards proving that that construction is actually optimal. But actually, as I'll mention in a second, we actually know that it's not rigid enough to prove a lower bound like this. But the result that I'm telling you about today of the smaller low depth circuits for the Walsh-Hadamard transform follows kind of a converse of Valiant's result. So the idea here is that we're going to use rigidity upper bounds for Kronecker products like the Walsh-Hadamard transform to give linear circuit upper bounds, whereas in contrast, less valiance result showed that if you have a small low depth circuit, then you get a rigidity upper bound from that. So the plan is sort of a converse of Les Valiant's plan. Okay, so what do we know about rigidity in the Walsh-Hadamard transform? Well, in joint work with Ryan Williams a few years ago, we showed that the Walsh-Hadamard transform is actually not rigid enough to prove lower bounds using Valiant's approach. So we showed that actually for any epsilon, you can change n to the 1 plus epsilon entries of the matrix to make its rank go all the way down to n to the 1 minus about epsilon squared. So it's actually, you can actually change this many entries and drop its rank to quite a bit lower than just n over log n, like Valiant's rigidity parameters needed. And from this, it's actually not too hard to get a depth 2 circuit construction for the Walsh-Hadamard transform. So rigidity upper bounds really naturally give rise to depth 2 constructions. The idea is just that if you have any matrix M and any rank R, and you compute the rank R rigidity of M, then you get a depth 2 circuit for M of size the rigidity plus 2 times n times R. And the idea is just from this rigidity upper bound, we know we can write the matrix as the sum of a low rank matrix, which we can factor like this, and a sparse matrix S. So the sparse matrix, the number of non-zero entries in it is the rigidity that we computed. So S corresponds to a depth 1 circuit of size the rank R rigidity of M. And then the low rank part, we can factor it as U times V, where U is an N by R matrix and V is an R by N matrix. And with some work, you can see this corresponds to a depth 2 circuit of size 2 times N times R. So in total, you get a circuit of this size for computing M, and you can balance as R gets bigger. This first term is bigger, but the rigidity gets smaller, so you can balance R and figure out what size upper bound you get out of this construction. And combining this with the rigidity upper bound up here for the Walsh-Hadamard transform, we can see that there's some constant delta bigger than 0, such that the Walsh-Hadamard transform has a depth 2 circuit of size n to the 2 minus delta. Okay, so you do immediately get some non-trivial construction from this rigidity upper bound. However, as I mentioned before, we actually already know that the Walsh-Hadamard transform has a depth 2 circuit of size n to the 1.5. And despite a fair bit of work, I wasn't able to figure out how to use this rigidity upper bound to actually improve on the n to the 1.5. So the new construction actually uses a different rigidity upper bound. So let me tell you the high level idea. So there's two new key ideas we use to design the smaller circuit for the Walsh-Hadamard transform. The first is a new observation that small circuits for any fixed matrix in the family of Walsh-Hadamard transforms implies small circuits for every Walsh-Hadamard transform. So it suffices to pick a fixed number k, like we end up picking like 4, and showing that if you have a small circuit for the kth Walsh-Hadamard transform, then you get small circuits for all increasingly big Walsh-Hadamard transforms as well. And this makes use of the Kronecker power definition of the Walsh-Hadamard transform. And then the second new idea is to use rigidity upper bounds to actually construct these small circuits for fixed matrices in the family. So we show here the parameters, the details are not super important, but you can fix any k, so any particular Walsh-Hadamard transform matrix, and any target rank R, and compute the rank R rigidity of HK. Then, using it, you can get a linear circuit of size d times n to the 1 plus c over d, where c is defined like this. It's this expression depending on k and r and the rigidity. And in particular, if you get a smaller upper bound on the rigidity of this Walsh-Hadamard transform, you get a better bound on the number c. And if you can get this number c to be some constant less than 1, then you have improved on the fast Walsh-Hadamard transform. So this construction basically comes from the idea I mentioned before, where rigidity upper bounds can give depth 2 circuit upper bounds combined with this first idea of using the particular small circuit for a fixed matrix to design small circuits for all increasingly larger matrices. And in fact, the rigidity upper bound we end up plugging in is not the one I told you about before, but a new upper bound showing that for the 16 by 16 Walsh-Hadamard transform, its rank 1 rigidity is at most 96. So we prove this new rigidity upper bound and plug it into this construction to give a new circuit upper bound for the Walsh-Hadamard transform. Okay, so let me say one more slide about this result and answer a few natural questions that you might have about what I just said. So the first question I think is, could we hope to design even smaller circuits from better rigidity upper bounds, better than this specific rank 1 rigidity of the 16 by 16 Walsh-Hadamard transform? And actually, I don't know how to rule this out in general. So I used a computer search to show that if you pick the rigid rank to be 1 or 2 and k to be at most 5, then you can't use the rigidity for in one of these small cases to improve the size of the circuits you get. And it seems like as these parameters are getting bigger, the constants you get in the construction are getting worse. But I don't know how to prove this. So the paper leaves open the possibility of actually improving the construction using a different rigidity upper bound. Okay. The next question is, what about other Kronecker powers other than just the Walsh-Hadamard transform? And in fact, we're able to show that for any family of matrices defined as Kronecker powers of any fixed matrix, fixed 2x2 matrix, you can show that as a depth 2 circuit of size just n to the 1.49 and a depth d circuit of size a little like d times n to the 1 plus some constant less than 1 over d. So you can roughly show that for any family of matrices like this, there is a good rigidity upper bound you can use, although a little bit worse than the one we can prove for the Walsh-Hadamard transform specifically. Okay, what about, so I've been talking about low depth like depth 2. What about for unbounded depth circuits? Well, we can use the same idea to improve the constant in the size of an unbounded depth circuit for the Walsh-Hadamard transform. So the fast Walsh-Hadamard transform algorithm gives a circuit of size about 1.88 times n log n. And these ideas can improve it to about 1.81 times n log n. And in fact, the same paper by Pudlock that showed that bounded coefficient circuit lower bounds for the Walsh-Hadamard transform also showed that you would need unbounded coefficient circuits even to improve this 1.88 constant. So unbounded coefficients are needed for a result like this, but we only improve it by a constant factor. And then what about other Fourier transforms, like the discrete Fourier transform with roots of unity in it that you might be more familiar with? Well, actually, known rigidity lower bounds rule out using this specific approach to improving on the fast Fourier transform. But, well, in the paper I discuss a little bit, there's other types of approaches that are slight variations on this that I don't know how to rule out and that might be helpful for speeding up the fast Fourier transform as well. Okay, let me finish by quickly mentioning one other result in the paper, and I mentioned there are even more results that I don't have enough time to talk to you about here in this video. But here's one more result. It's a new non-rigidity result, and it concerns matrices that are defined like this. So for any field f and any Boolean function that takes in a 0, 1 string of length n and outputs field values, let's define the matrix M sub f, that's a 2 to the n by 2 to the n matrix, like this. So you take in the row and column indices are 0, 1 vectors of length n, and that entry of the matrix is f applied to the bitwise and of x and y. So this is a family of matrices for any such function f. For example, when f is the parity function, you can see that this M sub f actually corresponds to the Walsh-Hadamard transform we've been talking about. But when f can be other functions, you can get a lot of different types of matrices. And another new result in the paper is that for any function f in any field, this matrix M sub f is not rigid enough to prove lower bounds using Valiant's approach. So you can change n to the 1 plus epsilon of its entries, and again make its rank like n to the 1 minus epsilon squared. So this generalizes the previous result from the non-rigidity of just the Walsh-Hadamard transform to any matrix that's defined like this, even for a very complicated function f. And one interesting property, I think, of the proof is that it doesn't make use of the polynomial method. So if you're familiar with the original proof that the Walsh-Hadamard transform is not rigid, it critically used the fact that you could design a low-degree polynomial approximation for the parity function f. But in fact, this new generalization shows that even if f is like a random function that for sure does not have a low-degree approximation, still the corresponding matrix is not rigid. So it's, I think, an interesting generalization of the previous result. All right, thanks for watching this video.